Welcome to the Sleepy Scientist. It's lovely to have you here. Before drifting into tonight's strange little corner of reality, take a moment to settle in. Maybe you're watching from a quiet room at the end of a long day, maybe from a sofa with the lights low, or maybe from somewhere much less sensible, like a train carriage where someone nearby has decided that crisp packets should be opened as dramatically as possible. Wherever you are, thank you for being here. If these calm science journeys help you relax, think, or gently fall asleep with slightly more knowledge than you had before, then a like and subscribe is always deeply appreciated. It helps this quiet little channel keep moving through the universe, one strange idea at a time. And if you're already subscribed, thank you. Truly. The idea we are about to meet is one that people often want to sit with a little longer, which is part of why there is a Sleepy Scientist ebook, Quantum Physics, Explained Clearly. It walks through ideas like this one slowly and patiently, the way a tricky concept deserves, and the full audiobook is included so you can read it or listen to it. The channel runs without ads, so these videos stay calm and uninterrupted, and supporting the ebook is one of the kindest ways to help keep it that way. The link is waiting quietly in the description. Tonight's topic is one of the most unsettling ideas in all of physics, though unsettling in a very polite, mathematically well-behaved sort of way. Quantum entanglement seems to suggest that two particles can share a connection so deep that measuring one tells you something about the other, even when they are separated by enormous distances. Not because a signal races between them like a tiny courier with excellent time management, and not because anyone can use it to send messages faster than light, but because quantum reality does not always divide itself into separate pieces as neatly as everyday common sense expects. So this evening, let's move slowly through the mystery. What is quantum entanglement? Why did Einstein find it so troubling? And how did experiments show that the universe really does contain a link that, at first glance, feels as if it should not exist? The world usually feels as if it is made of separate things. This sounds almost too obvious to say, which is usually where physics begins to look suspiciously at the furniture. A cup sits on a table. A book rests beside it. A lamp glows in the corner. Each object appears to have its own place, its own shape, its own history, and its own quiet independence. The cup does not seem to care whether the book is open or closed. The lamp does not flicker because a stone rolls down a hill on the other side of the planet. The table does not suddenly rearrange itself because a star, somewhere in the distant reaches of space, happens to collapse. This is the ordinary world, and it is wonderfully convincing. Everyday life teaches the mind to divide reality into individual pieces. A person has a position, a planet has an orbit, a falling apple has a speed, a direction, and a path through the air. A raindrop on a window can be watched as it slides down the glass, hesitates at a tiny ridge of dust, joins another drop, and becomes slightly heavier. Each thing seems to carry its own properties with it, as if nature has quietly attached a little invisible label to every object saying, "Here is what this is, here is where it is, here is what it is doing." That assumption is not foolish. In fact, it is one of the reasons human beings can move through the world at all. If chairs did not remain where they were a moment ago, sitting down would become a much more adventurous activity. If stones did not keep their weight, if doors did not keep their shape, if hot things did not remain hot long enough to be treated carefully, ordinary life would dissolve into chaos. The brain survives by expecting objects to have stable properties, and most of the time, at human scales, those expectations work beautifully. Classical physics grew from this kind of world. In the 17th century, Isaac Newton gave this everyday separateness a mathematical form. His laws of motion described how objects move when forces act on them. His law of universal gravitation described how every mass attracts every other mass. The same principles could explain a falling apple, a swinging pendulum, the motion of the moon, and the paths of planets around the sun. It was one of the great unifications in the history of thought. The heavens and the earth were not governed by separate rulebooks, as if the universe had a local council for apples and a royal charter for planets. They belonged to the same physical order. In Newton's picture, objects could be treated as definite things. A planet had a position and a velocity. A cannonball followed a trajectory. A clock ticked forward with a steady rhythm. Even when the calculations became complicated, the basic idea remained reassuring. If enough information were known, the future motion of a system could, in principle, be predicted. Nature might be difficult, but it was not vague. It did not seem to hesitate. This classical picture encouraged a very powerful assumption, that physical things have definite properties whether or not anyone observes them. The moon is not thought to vanish or lose its position when no one is looking at it. A mountain does not wait politely for attention before deciding how tall it is. A comet moving through the outer solar system does not require a telescope pointed at it before it has a path. Observation may reveal a property, disturb a delicate system, or improve a measurement, but in the ordinary classical view, it does not create the property from nothing. That distinction matters deeply. A thermometer placed in warm water may slightly affect the water, but the water was already warm. A speed camera may record the speed of a car, but the car was already moving. A ruler may be used to measure the length of a table, but the table was not waiting in a mysterious blur of possible lengths until someone arrived with stationery. Measurement, in this familiar picture, is a way of finding out what is already there. This is one of the quiet pillars of common sense. Another pillar is locality. Locality is the idea that physical influence must travel through space from one place to another. Something here can affect something there, but the influence needs a route. It may travel through a push, a pull, a wave, a field, a beam of light, a sound, a vibration, or some other physical process. But it does not simply appear instantly at a distance without crossing the space between. A candle can warm nearby air, but not a room on Mars. A stone dropped into a pond sends ripples outward, but the far edge of the pond only moves after the ripple reaches it. A voice travels as pressure waves through air. Light from the sun takes a little over 8 minutes to reach Earth. Even gravity, in the modern picture of Albert Einstein's general relativity, does not update the universe instantly. Changes in gravity travel at the speed of light, woven into the behavior of space-time itself. Locality makes the universe feel orderly. It gives cause and effect a kind of geography. Events are not just related by what happens, but by where and when influence can travel. A match lights a candle because flame touches the wick. The moon raises tides because its gravity acts across space in a lawful way. A radio antenna sends a signal because electromagnetic waves spread outward at a finite speed. There is always a path, even if the path is invisible. This is why entanglement feels so strange. The ordinary world appears to be built from separate things with their own properties, influenced by nearby causes or by signals that travel across space. That does not mean everything is isolated. Far from it. The universe is full of relationships. The Earth pulls on the moon. The sun lights the Earth. Air presses against skin. A hand can lift a cup. A magnet can attract iron filings. But these relationships still respect the idea that physical influence is carried through space by something, and that individual objects can be described on their own. Quantum entanglement seems to challenge that last part. It suggests that two particles can sometimes be described only as a shared system, even when they are far apart. Not because one is secretly sending a little message to the other, and not because they are connected by a tiny thread stretched across the cosmos, perhaps getting tangled around Saturn on the way. The problem is deeper and stranger than that. In an entangled quantum state, the full description belongs to the pair, not neatly to each particle by itself. This is difficult because it rubs against the instincts that classical physics trained so well. If two coins are placed in separate boxes, and one box is sent to London while the other is sent to Tokyo, There is nothing mysterious about opening one box and discovering the other coin must be the opposite side, if someone prepared them that way. If the London coin is heads, and the coins were arranged as opposites from the beginning, then the Tokyo coin is tails. That is ordinary correlation. The information was already there, quietly waiting inside the boxes. No one needs spooky influence, hidden cosmic gossip, or a panicked message sprinting across continents. Entanglement is not like that simple coin story. Quantum experiments indicate that the outcomes are correlated in ways that cannot be explained by each particle, merely carrying a fixed set of hidden answers from the start, at least not if those answers obey local classical rules. That is the heart of the discomfort. The link appears stronger than common sense allows, yet it cannot be used as a controllable faster than light signal. It is not ordinary communication, it is not ordinary separation, it is something else. Before that strangeness can be appreciated, the calm world of separate things has to be held clearly in mind. That world is not wrong in the places where it works. Newtonian mechanics still guides bridges, engines, falling objects, and spacecraft with remarkable accuracy when speeds are not too close to the speed of light and quantum effects are not dominant. Classical ideas remain some of the most successful approximations ever discovered. They are not embarrassing old furniture to be thrown out. They are more like a beautifully made map that works across familiar terrain until the road bends toward a place it was never designed to show. Quantum entanglement lives beyond that familiar terrain. It begins where the assumption of separateness becomes too simple. It asks whether the deepest description of reality is always built from independent parts, or whether at the smallest scales, relationships can be more fundamental than the objects being related. That is why the link feels as if it should not exist. Not because it is sloppy science or mystical decoration, or a dramatic phrase looking for attention, but because it violates a very old and very natural expectation. The world seems to be made of separate things. Quantum physics quietly replies that sometimes, at the deepest level, the separation was never as complete as it appeared. For a long time, classical physics seemed to offer a universe that was difficult but fundamentally understandable. Objects had positions. Forces acted on them. Light travelled through space. Heat flowed from hotter places to cooler ones. Matter was made of atoms, and atoms were imagined as tiny pieces of substance, perhaps not fully understood yet, but still belonging to the same broad family as stones, planets, and grains of dust. Then, very quietly at first, nature began to misbehave. The trouble did not begin because physicists wanted the universe to become strange. It began because experiments refused to fit the old explanations. Classical physics had not collapsed in some dramatic intellectual thunderstorm. It still worked beautifully for falling objects, engines, bridges, pendulums, and planets. But at very small scales, and in the behaviour of light and heat, small cracks began to appear. They were not large enough to destroy the whole building, but they were definitely large enough for a few concerned scientists to gather around them and say, rather politely, that something had gone wrong. One of the most important cracks appeared in the study of blackbody radiation. A blackbody is an idealized object that absorbs all incoming light and emits radiation depending on its temperature. It sounds like something that might sit ominously in a laboratory corner, but the basic idea is very ordinary. Hot things glow. Warm metal can shine red. A hotter flame can glow yellow or white. The colour and intensity of that glow reveal something about how energy is being emitted. By the late 19th century, physicists were trying to explain this glow using classical ideas. The problem was that the classical prediction failed badly at shorter wavelengths. It suggested that a hot object should emit an absurd amount of ultraviolet radiation, a result later nicknamed the ultraviolet catastrophe. The name is a little dramatic, though to be fair, if a theory predicts infinite ultraviolet energy, it has probably earned a theatrical title. In 1900, Max Planck found a way to solve the problem. He proposed that energy was not emitted or absorbed in any smooth, continuous amount, but in small discrete packets. These packets were later understood as quanta. Planck did not initially present this as a grand revolution in the nature of reality. It was more like a mathematical rescue mission, but the rescue worked too well to ignore. Energy, at least in this context, behaved as though it came in steps. That was deeply unsettling. In the ordinary world, energy seems to vary smoothly. A fire can burn a little warmer or a little cooler. A ball can roll a little faster or a little slower. A dimmer switch can make a lamp gradually brighter. But Planck's work suggested that, beneath the smooth appearance of things, nature might exchange energy in indivisible portions. Then Albert Einstein pushed the idea further. In 1905, Einstein studied the photoelectric effect, where light shining on certain metals can knock electrons out of the material. Classical wave theory expected that brighter light should give electrons more energy, because a stronger wave should deliver a stronger push. But experiments showed something more surprising. The colour or frequency of the light mattered in a very direct way. Below a certain frequency, no electrons were emitted, no matter how bright the light became. Above that threshold, electrons could be released even by weak light. Einstein explained this by treating light as if it came in particle-like packets of energy, later called photons. Each photon carried an amount of energy tied to the light's frequency. If a photon had enough energy, it could free an electron. If it did not, adding more low-frequency photons would not help in the same way. It was a little like trying to open a locked door with coins that were all too small for the slot. Having a bucket of them is impressive, but the door remains calmly unimpressed. This did something strange to the status of light. Light had already been described beautifully as a wave by James Clerk Maxwell's electromagnetic theory. It could interfere, diffract, and spread in ways waves naturally do. Yet Einstein's explanation showed that light also behaved as if it came in individual particles. It was not simply one or the other in the familiar sense. The categories were beginning to blur. The next difficulty lived inside the atom itself. By the early 20th century, Ernest Rutherford's work had shown that atoms contain a small, dense, positively charged nucleus, with electrons associated with the space around it. But this created a serious problem. According to classical electromagnetism, an electron moving around a nucleus should radiate energy. As it lost energy, it should spiral inward. Atoms should collapse almost immediately. Ordinary matter should not be stable. Tables, stars, skin, books, and sleepy cups of tea should not hold together in the familiar way. Clearly something was missing, because matter was quite stubbornly existing. In 1913, Niels Bohr proposed an early quantum model of the atom. He suggested that electrons could occupy only certain allowed energy levels, rather than any possible orbit. When electrons moved between these levels, they absorbed or emitted energy in definite amounts. This helped explain the spectral lines of hydrogen, the precise colours of light emitted or absorbed by hydrogen atoms. Instead of producing a continuous smear of colour, atoms revealed sharp signatures like tiny cosmic barcodes. Bohr's model was not the final version of atomic theory, but it was a crucial step. It showed that the stability of atoms depended on rules very different from classical expectations. Electrons were not simply tiny planets orbiting a miniature sun. The atom was not a small solar system, however tempting that picture remains. At quantum scales, only certain states were allowed, and nature seemed to choose from a set of permitted possibilities. Then came Louis de Broglie, who made the situation even more peculiar. If light, long understood as a wave, could behave like a particle, de Broglie wondered whether matter, long understood as particle-like, could behave like a wave. In 1924, he proposed that particles such as electrons have wave-like properties. This idea was later supported experimentally when electrons were shown to produce diffraction patterns, a behaviour normally associated with waves passing through openings or around obstacles. This was not just a decorative mystery. Wave-particle duality meant that the old boundary between object and wave was no longer secure. Light could arrive in photon packets, yet also interfere like a wave. Electrons could be detected as individual particles, yet their behaviour could only be fully predicted using wave-like mathematics. Reality had not become nonsense, but it had stopped fitting into the tidy boxes that everyday experience had provided. That is the key point. Quantum theory did not begin as an attempt to make physics sound mystical, poetic, or deliberately confusing. It began because black-body radiation, the photoelectric effect, atomic spectra, and matter waves forced physicists to accept that classical mechanics was incomplete. Each discovery was tied to real measurements. Each idea emerged because nature had left evidence that could not be ignored. The world of separate things was still there. Cups, planets, lamps, and falling stones had not vanished. But beneath that familiar surface, physics was revealing a deeper layer where energy came in quanta. Light behaved like both wave and particle. Atoms survived through discrete energy levels, and matter itself carried wave-like behaviour. The path toward entanglement begins in this blurring. Once particles are no longer simple little objects with ready-made properties, once measurement becomes part of the story, and once waves of possibility enter the description of matter, the ordinary idea of separateness begins to loosen, not break all at once, not disappear, but loosen, quietly and profoundly, like a knot that had always seemed permanent until someone finally noticed the hidden thread. The early discoveries of quantum physics revealed that light, energy, and matter were not behaving quite as classical physics expected. Energy could arrive in packets. Light could act like a wave in one experiment, and like a stream of photons in another. Electrons inside atoms did not spiral helplessly into the nucleus, even though older theory suggested they should. Matter itself could show wave-like behaviour, as if the universe had quietly decided that the boundary between object and ripple was not going to be as tidy as anyone had hoped. To make sense of all this, physicists needed a new language. That language became the wave function. The wave function is one of the central ideas in quantum mechanics. It is a mathematical description of a quantum system used to describe the possible states that a system can have before a measurement gives a definite result. It does not behave like an ordinary photograph of an object. It is not a little picture showing exactly where an electron is, what it is doing, and which tiny chair it has chosen to sit on. Instead, it gives a structured description of possibilities. This was a major shift. In classical physics, the ideal description of a moving object would include definite properties, such as position and velocity. A thrown stone has a path. A planet has an orbit. A clock pendulum swings through space in a way that can be described with remarkable precision. But in quantum mechanics, the most complete description available before measurement does not always assign one neat outcome in advance. It gives a spread of possibilities, each with a probability attached. In the mid-1920s, two powerful versions of quantum theory appeared almost side by side. Werner Heisenberg developed matrix mechanics in 1925. This approach was abstract and mathematical, focusing on measurable quantities such as the frequencies and intensities of light emitted by atoms. It did not try to picture electrons moving in familiar little orbits. In fact, it was almost deliberately unfriendly to ordinary visual imagination, as if physics had decided that diagrams had become too comfortable. Then Erwin Schrödinger developed wave mechanics in 1926. His version used wave equations to describe quantum systems, and at first it seemed easier to imagine. Electrons could be associated with waves rather than tiny orbiting balls. Atomic states could be described as wave patterns. It offered a smoother, more visual way into the quantum world. At first glance, Heisenberg's matrix mechanics and Schrödinger's wave mechanics looked very different. One seemed abstract and algebraic. The other seemed more wave-like and continuous. but they were soon shown to be mathematically equivalent. They were different routes through the same strange landscape. The universe had not handed physicists two different rulebooks. It had handed them one rulebook written in more than one dialect, which is considerate in one sense and deeply inconvenient in another. The next question was what the wave function actually meant. This is where Max Born made a decisive contribution. In 1926, Born proposed the probability interpretation of the wave function. According to this interpretation, the wave function does not simply describe a physical ripple spread through ordinary space in the same way water ripples across a pond. Instead, it gives the probabilities for different measurement outcomes. It tells physicists how likely it is that a particle will be found here rather than there, or in one state rather than another, when a measurement is made. This was not merely a technical adjustment. It changed the emotional temperature of physics. Probability had appeared in science before, of course. Weather forecasts use probability. Gambling uses probability. A shuffled deck of cards can be described with probability if the order is unknown. But in those familiar cases, probability often reflects ignorance. The card already has a fixed identity before anyone turns it over. The uncertainty belongs to the person, not necessarily to the card. The card is not undecided. It is just being secretive, which is a much more ordinary kind of rudeness. Quantum probability appears to be deeper than that. In standard quantum mechanics, before measurement, a system is not always described as secretly having one definite value that the observer simply does not know. Instead, the wave function can describe a superposition of possible outcomes. Superposition means that a quantum system is represented as a combination of different possible states at once. An electron may not have one definite measured position before interaction. A photon may not have one definite polarization outcome waiting like a card in an envelope. The theory describes a range of possibilities, and measurement produces one recorded result. This does not mean anything can happen without rules. Quantum mechanics is not a cosmic shrug. The wave function evolves according to precise mathematical laws, and its probabilities can be tested with extraordinary accuracy. The strange part is not that quantum theory is vague in its predictions. The strange part is that it predicts probabilities with astonishing precision, while refusing to behave like a simple catalogue of pre-existing properties. That distinction matters for entanglement. If quantum systems were always just little objects carrying complete property lists, then the world would remain comfortably classical beneath the surface. Measurement would simply reveal whatever had already been written down in tiny invisible ink. But the wave function suggests something more subtle. It describes the state of a system as a whole. And sometimes, when more than one particle is involved, the whole system cannot be broken cleanly into independent descriptions of each part. This is the first quiet step toward entanglement. A single particle can already challenge ordinary thinking by existing in a superposition of possible measurement outcomes. But when two particles are described by one combined wave function, the strangeness deepens. Their possible outcomes can become linked inside the shared mathematical state. The complete description may belong not to particle 1 and particle 2 separately, but to the pair together. This is not yet the dramatic image of distant particles seeming to know about one another across space. It is the groundwork beneath that image. Quantum mechanics first asks the listener to accept that possibility is not always just ignorance, that measurement is not always passive discovery, and that the wave function may describe reality in a way that has no simple everyday equivalent. The old world of separate objects has not vanished. It still works beautifully for cups, stones, lamps, and planets. But beneath it, quantum theory speaks in a quieter language of possible outcomes, shared states, and probabilities that are not merely gaps in human knowledge. And once reality can be described this way, the idea of two particles sharing one combined state no longer sounds like an added absurdity. It sounds like the next strange sentence in a language physics had already begun to learn. Entanglement begins with the deceptively simple idea. In quantum physics, the full description of a system is not always made by describing each part separately. That sounds harmless at first. After all, many ordinary things are described as wholes. A flock of birds has a shape, a choir has a harmony, a weather system has a swirling structure that cannot be understood by staring at one raindrop with heroic determination. But quantum entanglement is stranger than ordinary togetherness. It is not just that two particles have interacted, or that they once shared a past. It is that the properties measured from them can be described by one shared quantum state. So the whole system cannot be fully reduced to two independent little property lists. This is where the wave function becomes more than a language of possibility for one object. In some cases, the wave function belongs to the combined system more deeply than it belongs to each part alone. Instead of saying particle 1 has its own complete state and particle 2 has its own complete state, quantum mechanics sometimes says that the pair has a state. The relationship is not an extra detail added after the particles are described. The relationship is part of the description itself. That is quantum entanglement. It does not mean two particles are tied together by a visible thread. There is no tiny glowing string stretched between them, no little force line humming through space, and no secret wire quietly embarrassing itself across the universe. Entanglement is not a mechanical attachment. It is not a signal cable. It is not a mystical sympathy between particles that care about each other's emotional well-being, which is probably for the best, since electrons already have enough to do. The clearest way to approach it is through measurement. Imagine two particles created together in a way that links a property such as spin. Spin is a real quantum property related to angular momentum and magnetic behavior, though it is not simply a tiny ball rotating like a planet. When physicists measure spin along a chosen direction, the result comes in definite outcomes. For certain entangled pairs, if one particle is measured and gives one result, the other particle will give a related result when measured in the same way. At first that may not sound mysterious. Ordinary objects can be correlated too. Imagine a pair of gloves placed into two boxes. One box is sent to one city, the other box to another city. When someone opens the first box and finds a left-handed glove, they immediately know the other box contains the right-handed glove. Nothing spooky has happened. The gloves had their properties all along. The discovery in one place simply reveals information about the other place. This is classical correlation. It is surprising only if the observer did not know how the boxes were packed. Entanglement is different. The results of quantum experiments cannot be explained as simply as two particles carrying fixed hidden answers from the beginning, at least not if those answers obey the ordinary classical rule of locality. The particles are not merely like gloves that already knew what they were before anyone opened the boxes, nor are they like sealed envelopes containing a complete set of instructions for every possible measurement. That picture feels comforting, but it does not match the full pattern of quantum correlations measured in experiments. The difference appears when physicists vary the way they measure the particles. With ordinary hidden instructions, there are limits to how strongly the results can line up across different measurement choices. Quantum mechanics predicts correlations stronger than those classical limits allow, and real experiments have repeatedly supported the quantum prediction. This is why entanglement is not just a poetic name for two things being connected. It is a measurable feature of nature. Still, it is important to say what entanglement is not. Entanglement is not mystical communication. It is not conscious intention. It does not mean one particle decides what the other particle should do, like a very small manager with no clipboard but enormous confidence. It does not allow people to send messages instantly across space. The individual result of a measurement still appears random to the observer who receives it. The strange connection only becomes visible when the results from both sides are compared. That is part of what makes entanglement so subtle. It seems to involve a deep connection across distance, yet it does not behave like ordinary communication. It challenges the idea that separated particles must each carry their own, complete independent reality, but it does not turn the universe into a faster-than-light messaging service. The phrase "the link that should not exist" captures this tension. From the point of view of everyday intuition, distant things should either be independent or they should affect each other through some influence travelling between them. Entanglement seems to resist both easy categories. The particles are not fully independent in the way classical separateness expects. Yet there is no usable signal flashing between them faster than light. The link is real, but it's not a link in the ordinary mechanical sense. A helpful way to think about it is to stop imagining the particles first and the relationship second. In ordinary thought, the mind wants to picture two separate objects, then add a connection between them. Quantum mechanics sometimes asks for something less familiar. It describes the combined system first. The separate measurement outcomes appear when interactions with measuring devices force definite results to be recorded. This does not make entanglement vague or imaginary. It is one of the most precisely tested features of quantum physics. The difficulty lies not in whether the correlations exist, but in how to picture what they mean. Common sense wants the world to be made of separate pieces with their own finished properties. Quantum theory replies that, at small scales, the whole can be more fundamental than the parts. And that is why entanglement sits so close to the heart of the quantum mystery. It is not simply two particles behaving oddly. It is a sign that reality does not always begin with isolated objects and then build relationships between them. Sometimes the shared state comes first, and the separate facts arrive only when the world is measured. By the middle of the 1930s, quantum mechanics had become one of the most successful theories in science, and also one of the most uncomfortable. It explained atomic spectra. It explained why electrons occupied particular energy levels. It gave physicists a working language for light, matter, probability, and measurement. It did not feel like a vague philosophical suggestion floating around in a smoky room, nodding mysteriously at itself. It made real predictions, and those predictions matched real experiments. In that sense, quantum mechanics was not weak. It was almost annoyingly strong. But success is not the same as satisfaction. Albert Einstein had helped build the quantum revolution. His work on the photoelectric effect in 1905 had been one of the key steps toward the idea that light could behave as if it came in particle-like packets, later called photons. He was not simply an old classical thinker grumbling at a new generation because reality had changed the furniture. Einstein understood quantum theory deeply. His problem was not that quantum mechanics failed. His problem was that it seemed to succeed while leaving something essential unexplained. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a famous paper arguing that quantum mechanics might be incomplete. Their argument was not about whether the theory gave useful results. It plainly did. The question was whether it gave a complete description of physical reality. The concern began with a simple but powerful expectation. If two systems are far apart, then something done to one should not instantly change the real physical condition of the other. This is the principle of locality, the idea that physical influence should travel through space rather than leap across it without a route. It fits beautifully with the ordinary world. A stone dropped into water sends ripples outward. A radio antenna sends electromagnetic waves. A lamp lights a room by sending light through space. Even in Einstein's own theory of relativity, usable influence cannot travel faster than light. Entanglement seemed to press on this expectation in a very awkward way. If two quantum systems had once interacted and were then separated, quantum mechanics could describe them with one shared state. Measuring one system could allow a physicist to predict something about the other. To Einstein, Podolsky, and Rosen, this raised a troubling dilemma. Either the act of measurement on one system somehow had an immediate connection with the distant system, or the distant system already possessed definite properties that quantum mechanics was failing to describe. This second possibility was the more comfortable one for Einstein. Perhaps quantum mechanics was not wrong, but incomplete. Perhaps the wave function was not the full story. It might be like a weather forecast that gives excellent probabilities, because the atmosphere is too complex to track perfectly, while the atmosphere itself still has definite conditions underneath. In that view, quantum uncertainty would reflect missing information, not a deep feature of nature. This is where Einstein's discomfort became famous. He later objected to what is often called spooky action at a distance. The phrase is memorable because it captures the unease so well. Physics, in Einstein's view, should not require distant systems to behave as if one measurement here instantly reaches out and settles something over there. The universe should not behave like a magician who has learned mathematics and refuses to explain the trick. But it is important to be fair to him. Einstein was not rejecting experiments, and he was not simply offended by strangeness. He had already accepted some deeply strange ideas when evidence demanded them. Special relativity had changed the meaning of space and time. General relativity had turned gravity into the curvature of space-time. Einstein was perfectly capable of following reality into unfamiliar territory. His objection was sharper than simple dislike. He wanted a theory that preserved a clear idea of physical reality, where objects had definite properties, and distant events could not instantly alter one another in a way that seemed to violate locality. Niels Bohr responded quickly to the 1935 paper. Bohr defended quantum mechanics, but his response was not that Einstein, Podolsky and Rosen had found a minor technical mistake, and everyone could go home for tea. Bohr argued that quantum phenomena could not be separated so easily from the entire measurement arrangement. In his view, the meaning of a measured quantity depended on the experimental context used to define and observe it. A quantum system was not simply carrying a full list of ordinary properties before measurement, waiting for someone to read them off. This disagreement reflected one of the deepest divides in 20th century physics. Einstein wanted a description of reality that existed clearly and independently, even before observation. Bohr emphasized the inseparability of quantum phenomena from the conditions under which they are measured. To Bohr, the demand for classical-style definite properties before measurement might be asking the quantum world to provide something it does not possess in that form. The debate was not merely philosophical decoration. It was not a late-night argument about words, the sort that begins with reality and somehow ends with someone claiming chairs are a social construct. It concerned what a scientific theory is supposed to do. Should a complete theory describe what exists, whether measured or not, or should it describe the outcomes of experiments and the conditions under which those outcomes can be meaningfully discussed? Quantum entanglement sharpened this question because it made the problem impossible to ignore. A single quantum particle already challenged classical thinking through probability and superposition. But two entangled particles raised the stakes. If the pair had one shared state, and measurements on the separated parts produced stronger connections than ordinary separateness seemed to allow, then the issue was not just strange, it was foundational. The central question became unavoidable. Was entanglement revealing a missing layer beneath quantum mechanics, some deeper set of hidden facts that would restore a more familiar kind of reality? Or was it showing that the familiar picture itself was too limited, and that nature genuinely allows shared quantum states that cannot be reduced to separate independent parts? Einstein, Podolsky, Rosen, and Bohr did not settle the question in 1935. What they did was frame it so clearly that later physicists could not simply shrug it away. The argument turned entanglement from a curious mathematical feature into a direct challenge about reality, locality, measurement, and completeness. The link that should not exist had become more than a mystery. It had become a test of what physics was really trying to describe. The argument raised by Einstein, Podolsky, and Rosen left physicists with a very tempting possibility. Perhaps quantum mechanics was not the final layer of the story. Perhaps it worked beautifully because it was an excellent surface description, but beneath it there might be a deeper mechanism, a set of hidden details that would restore the older comfort of definite properties and local causes. These proposed deeper details became known as hidden variables. A hidden variable theory is an attempt to explain quantum outcomes by suggesting that particles or systems may have additional properties not included in the standard wave function. These properties would determine, or at least help determine, what result appears when a measurement is made. In this view, quantum randomness would not be truly fundamental. It would look random only because the underlying information was missing from the usual description. The appeal is easy to understand. Ordinary life is full of cases where uncertainty comes from not knowing enough. A weather forecast gives probabilities because the atmosphere is too vast and sensitive to measure perfectly. The rain does not appear because the clouds suddenly choose one possible reality during a dramatic philosophical moment. The weather follows physical processes, but too many details are involved for perfect prediction. The uncertainty comes from limited knowledge, not from nature being undecided in some deep way. A sealed mechanical device can feel similar. Imagine a small clockwork machine hidden inside a box. It clicks, turns, pauses, and produces one of several possible results when a lever is pulled. To someone outside the box, the outcome may seem random, but if the exact arrangement of gears, springs, and starting positions were known, the result might be predictable. The randomness belongs to the observer's ignorance, not necessarily to the machine itself. For many physicists, hidden variables offered a way to imagine quantum mechanics like that. The wave function might be useful, even brilliantly useful, but incomplete. The particle might still have a definite condition underneath the probability. Measurement might reveal an outcome determined by facts that standard quantum mechanics had not included. This did not mean quantum mechanics had failed experimentally. That was never the main issue. By the mid-20th century, quantum theory had already become astonishingly successful. It explained atomic structure, chemical bonding, spectra, and the behavior of electrons in matter. The question was subtler. Was quantum mechanics the deepest description available in principle, or was it a remarkably accurate statistical account of something more definite underneath? One of the most serious hidden variable theories was developed by David Bohm in 1952. Bohm's pilot wave theory, also known as Bohmian mechanics, gave a very different picture of quantum reality while reproducing many of the same predictions as standard quantum mechanics. In this approach, particles have definite positions, but they are guided by a wave-like object sometimes called the pilot wave. The particle does not merely drift through space in the old classical way. Its motion is shaped by the guiding wave, which encodes information about the wider quantum system. This was not a casual idea scribbled on the back of an envelope by someone trying to rescue common sense during a difficult afternoon. Bohm's theory was mathematically serious. It showed that at least some kind of deeper hidden variable picture could be built. It also made clear that the foundations of quantum mechanics were not settled simply because the standard theory worked. There were still different ways to imagine what might be happening beneath the calculations. But Bohm's theory came with a crucial feature. It was non-local. That word matters enormously. A local hidden variable theory would preserve the idea that distant events cannot instantly influence one another. In such a theory, the outcomes of measurements on separated particles would be determined by hidden properties carried with them from their shared past, or by influences travelling no faster than light. This would restore much of the older classical picture. The particles would still be separate things with complete underlying facts, and distant measurements would not need any immediate connection. A non-local hidden variable theory is different. It may still propose deeper underlying properties, but it allows the behavior of one part of the system to depend in some way on the wider arrangement, even across distance. Bohmian mechanics does this. It restores definite particle positions, but it does not restore the full classical dream of local separateness. The theory keeps a deeper mechanism, but the price is that the mechanism is not local in the ordinary classical sense. This distinction between local and non-local hidden variables became essential. Einstein's deepest discomfort was not only with randomness, it was with the apparent threat to locality. He wanted a theory in which reality was both complete and local, where distant objects had definite properties and did not require instant influence across space. A hidden variable theory that was non-local solved one part of the unease, while leaving another part very much alive. Still, hidden variables remained attractive because they offered a kind of rescue path. They suggested that the strange probabilities of quantum mechanics might be like the probabilities in weather forecasting, or the uncertainty around a sealed mechanism. Perhaps particles really did have definite properties all along. Perhaps the wave function simply did not tell the whole story. Perhaps the universe was not fundamentally rolling dice, but hiding some of the dice under the table, which is admittedly rude behaviour for a universe, but at least understandable. The Einstein, Podolsky and Rosen argument made this hope feel urgent. Entanglement had exposed a strange connection between distant measurements. If quantum mechanics was complete, then the familiar idea of separately existing properties seemed to be in trouble. If quantum mechanics was incomplete, hidden variables might explain the correlations without accepting such a radical change in reality. For a while, this seemed like a matter of interpretation, taste, and philosophical preference. Some physicists accepted the standard quantum picture. Others suspected a deeper layer. The debate could have remained suspended there, floating quietly between mathematics and metaphysics. But the hidden variable question would not stay safely philosophical forever. The crucial issue was whether local hidden variables could reproduce the predictions of quantum mechanics. If they could, then perhaps the old instincts about separateness and locality might survive. If they could not, then nature itself would be saying something far stranger. Hidden variables were the hope that quantum mechanics was not the final word. They were the hope that beneath probability there might still be a hidden machinery, precise and definite, patiently turning out the results that experiments recorded. But that hope was about to meet one of the sharpest tests in the history of physics. The hope behind hidden variables was not unreasonable. It came from a very old scientific instinct. When something appears random, perhaps the missing piece is not in nature, but in the observer's knowledge. A tossed coin seems unpredictable if the starting motion, air resistance, impact, spin, and surface are not known with enough precision. A weather forecast uses probabilities because the atmosphere is too intricate to track perfectly. A sealed machine may look mysterious from the outside, while gears and springs quietly determine everything inside. For some physicists, quantum mechanics might have been like that sealed machine. Then John Stuart Bell changed the shape of the argument. In 1964, Bell published a paper on the Einstein, Podolsky and Rosen paradox that turned one of the deepest philosophical questions in quantum physics into something that could be tested. This was the great leap. Before Bell, arguments about hidden variables, locality, and completeness could seem like questions of interpretation. One physicist might prefer Bohr's view, another might sympathize with Einstein. Someone else might want to hide quietly behind the blackboard until the argument was over, which was emotionally understandable, if not especially useful. Bell did something far more precise. He asked what the world should look like if local hidden variables were correct. Local hidden variables combine two ideas. The first is that particles have deeper properties not described by standard quantum mechanics. These hidden properties would help determine the results of measurements. The second is locality, the idea that what happens to one particle cannot instantly affect another distant particle in a usable physical way. Together, these ideas preserve much of the older classical picture. The particles may be strange, but they still carry their own deeper facts, and distant events do not have to reach across space immediately. Bell realized that this picture leads to limits on the correlations that can appear between measurements on entangled particles. These limits are now known as Bell inequalities. In plain language, Bell inequalities are boundaries. They say that if two distant particles are only connected by shared hidden information from their past, and if no faster than the light influence passes between them during the measurements, then their results can line up only so strongly. They may be correlated, certainly. They may behave like the paired gloves in separate boxes, where finding a left-handed glove in one place tells you the other box contains the right-handed glove. But there is a maximum strength to this kind of classical correlation when different measurement choices are included. Quantum mechanics predicts something stronger. For entangled particles, quantum theory says that measurement results can violate Bell inequalities. That means the particles can show correlations stronger than any local hidden variable theory allows. Not stronger in a vague poetic sense, stronger in a specific measurable way. Experiments can count the outcomes, compare the patterns, and ask whether nature follows the limits expected by local hidden variables, or the more unusual predictions of quantum mechanics. This is why Bell's theorem is so important. It did not merely add another opinion to the debate. It placed a boundary around what kinds of deeper explanations could still survive. If experiments obeyed Bell inequalities, then local hidden variables might remain a strong possibility. If experiments violated them in the way quantum mechanics predicted, then any deeper explanation would have to give up something important, especially the comforting idea of local separateness. Bell did not prove that no hidden variable theory of any kind could ever exist. That distinction matters. David Bohm's pilot wave theory, for example, is a hidden variable theory, but it is non-local. Bell's theorem is especially devastating for local hidden variable theories, the kind that would have restored both definite underlying properties and ordinary locality. It showed that Einstein's preferred combination was not merely difficult, it made predictions that could be checked against the world. That was the quiet brilliance of Bell's work. He took a question that sounded almost impossible to settle and gave it experimental teeth. Instead of asking only what reality ought to be like, physicists could ask what correlations actually appear when entangled particles are measured under carefully chosen conditions. The mathematics behind Bell's theorem can become technical, but the principle is beautifully clear. Imagine two observers far apart, each measuring one particle from an entangled pair. Each observer can choose between different measurement settings. If the particles carry local hidden instructions, then the pattern of answers across many repeated trials must obey certain limits. Quantum mechanics predicts that those limits will be exceeded. Reality is then asked to choose. This made the Einstein, Podolsky and Rosen debate much sharper. The question was no longer only whether quantum mechanics felt complete, or whether its view of measurement seemed philosophically satisfying. The question became whether the world behaves like a locally hidden mechanism or like quantum theory says it does. Bell's theorem is one of the great moments in modern physics because it shows how careful reasoning can turn an argument about reality into an experiment. It does not remove all mystery. In some ways, it deepens it. But it removes a certain kind of escape. If nature violates Bell inequalities, then the simple hope that particles merely carry hidden local answers from the start cannot explain the results. The link that should not exist had become testable. Bell did not settle the argument by declaring a winner from an armchair. He gave physics a way to listen to nature directly. The old hope of local hidden variables had been written into a form that laboratories could challenge. And once that happened, the mystery of entanglement was no longer only a strange implication of equations. It became a question waiting under glass, mirrors, detectors, and beams of light, ready for reality itself to answer. Bell's theorem changed the question from what physicists preferred to believe into what nature could be asked to reveal. That was its quiet power. A debate that had once lived mostly in thought experiments, philosophical arguments, and carefully written papers could now be carried into the laboratory, where light sources, mirrors, detectors, and patient measurement would do something that words alone could not. The key was to create pairs of entangled particles and measure them under controlled conditions. Photons became especially useful for this, because they are easy to send across a laboratory, and because one of their properties, polarization, can be measured with optical equipment. Polarization describes the orientation of a light wave's electric field, and although the full quantum meaning is more subtle than a simple arrow drawn on a page, It gives experimenters a practical property to test. The basic plan was beautifully direct. Produce pairs of photons whose polarizations are entangled. Send them in different directions towards separated detectors. Choose measurement settings for each detector. Then record the outcomes over and over again, not once or twice, but many thousands of times, until a statistical pattern appears. That pattern can then be compared with what local hidden variable theories allow and what quantum mechanics predicts. This was the point where the strange link became measurable. In 1972, John Clauser and Stuart Friedman carried out one of the first major experimental tests of Bell's ideas at the University of California, Berkeley. Their experiment used pairs of photons produced by excited calcium atoms. The photons travelled toward polarizing filters and detectors where their polarization correlations could be measured. The results supported the quantum prediction and provided important evidence that Bell inequalities were being violated. That result mattered enormously. It did not prove every philosophical interpretation of quantum mechanics correct, and it did not mean all possible questions had been settled forever. But it showed that Bell's theorem was not just an elegant theoretical exercise. It could be tested. More importantly, the test did not favour the comfortable local hidden variable picture that many had hoped might lie beneath quantum mechanics. Still, experiments are never perfect little windows into truth, polished by angels and placed gently on a laboratory bench. They involve equipment, limitations, noise, alignment problems, detector efficiencies, and enough cables to make any sensible person question the life choices of experimental physicists. This is why loopholes mattered. A loophole is not just an excuse. It is a possible technical weakness that leaves room for an alternative explanation. In Bell tests, one concern was detector efficiency. If many photons are missed, then the detected sample might not represent the full set of emitted photon pairs. Another concern was whether the two measurement events were separated well enough. If some ordinary signal travelling at or below the speed of light could pass between detectors, then perhaps hidden communication could still explain the correlation. A further concern involved how measurement settings were chosen and whether those choices were genuinely independent of the particles being measured. These details sound fussy, but they are exactly what makes experimental science powerful. The stranger the claim, the more carefully the door must be checked for little gaps around the frame. In the early 1980s, Alain Aspect and his colleagues in France carried out a series of more refined Bell test experiments. These included work with Philippe Grangier, Gérard Roget, and Jean Dalibard. Their experiments again used entangled photons and polarization measurements, but they improved the design in crucial ways. In one especially important version, the measurement settings were changed while the photons were already in flight. This made it harder to imagine that the particles could somehow have known in advance which exact measurements they would face, at least in any simple local hidden variable picture. The Aspect experiments became landmarks because they brought Bell's test closer to the spirit of the original challenge. They did not remove every possible loophole, but they strongly reinforced the evidence that nature violates Bell inequalities. The correlations found in the lab matched quantum mechanics more closely than the expectations of local hidden variable theories. The technology behind these experiments was not just background decoration. Optical physics made the question physically answerable. Photon sources had to produce suitable pairs. Polarizers had to measure polarization in chosen directions. Detectors had to register tiny flashes of light reliably enough to build up meaningful statistics. Timing electronics had to compare which detections belonged together. None of this was mystical. The mystery entered through the results, not through carelessness in the method, and the results had to be understood carefully. These experiments did not show that people can send ordinary messages faster than light. They did not show that one detector can be used like a telegraph to control the other detector across space. Each individual measurement result still appears random. The strange part is not that one scientist can choose a result here and make a chosen result appear over there. The strange part is that when both sets of results are later compared, the correlations are stronger than local hidden variable theories can explain. That distinction keeps the science honest. Entanglement does not break relativity in the everyday sense of usable signals racing across the universe, but it does break the older expectation that distant particles must behave as though all their measurable properties were settled locally from the start. This is why the experimental story is so important. Bell had shown that the argument could not remain safely abstract. Clauser, Friedman, Aspect, Grangier, Roger, Dalibard, and others helped show that the universe was willing to answer. The answer was not vague. It appeared in counts, correlations, polarization angles, detector clicks, and statistical patterns. A question that once seemed almost too strange for experiment had become a measurement made with real equipment on real benches. The link that should not exist had moved from thought to apparatus, from argument to data, from a troubling possibility inside equations to a pattern recorded in light. The early tests of Bell's theorem were persuasive, but science is at its best when it refuses to stop at persuasive. A result can be impressive, elegant, and deeply suggestive, while still leaving small technical doors open. In a subject as strange as entanglement, those doors mattered. The first Bell test experiments had already pointed strongly toward quantum mechanics. John Clauser and Stuart Friedman had found evidence in the early 1970s that the measured correlations between entangled photons violated Bell inequalities. Alain Aspect and his colleagues improved the situation in the early 1980s, especially by changing measurement settings while photons were already in flight. The results became harder and harder to explain using local hidden variables, but harder is not the same as impossible. A determined defender of local hidden variables could still ask whether some experimental weakness had allowed the quantum result to appear. Perhaps the detectors missed too many particles. Perhaps the measurement choices were not separated enough from the outcomes. Perhaps the particles, the detectors, or the settings were somehow connected through ordinary signals travelling at or below the speed of light. These suggestions may sound like desperate escape routes, but in physics, even a desperate escape route deserves to have its door measured, locked, and politely labelled. These possible weaknesses became known as loopholes. One of the most important was the locality loophole. Locality in this context means that the measurement choice made on one side of the experiment should not be able to influence the result on the other side by any ordinary signal moving at the speed of light or slower. To close this loophole, the experiment must arrange the measurements so that the choice of setting and the recording of the result happen with enough separation in space and time. In simple terms, the particles should not have time to whisper to each other, even if they were extremely punctual photons with a suspiciously strong work ethic. Another major issue was the detection loophole. In real experiments, not every particle is successfully detected. If many particles are missed, then the sample that is recorded might be biased. It might not represent the whole set of particles produced by the source. A local hidden variable explanation could then try to hide in the missing data, suggesting that the particles which were actually detected were a special subset. Closing the detection loophole requires detectors efficient enough and experimental designs careful enough that the recorded results cannot easily be dismissed as a skewed sample. Then there is the freedom of choice loophole. This one asks whether the measurement settings are genuinely independent of the hidden properties of the particles. In ordinary language, the concern is that the particles and the measurement choices might have been secretly coordinated in advance. If that sounds almost conspiratorial, that is because it is, but not in a silly way. Bell tests are so foundational that physicists tried to examine even very unlikely possibilities. The question was whether the settings used by the experimenters could be chosen in a way that was not already linked to whatever hidden variables might have travelled with the particles. By 2015, several major experiments had pushed Bell tests to a new level. Teams associated with Delft University of Technology, the National Institute of Standards and Technology, and the University of Vienna performed experiments often described as loophole-free Bell tests. Each used different physical systems and designs. but together they marked a major turning point. They showed violations of Bell inequalities while closing the most important experimental loopholes that had limited earlier tests. At Delft University of Technology, researchers used entangled electron spins associated with defects in diamond, separated by more than a kilometre. This allowed the team to address locality, while also obtaining reliable detection of the quantum systems involved. The National Institute of Standards and Technology and the University of Vienna performed highly efficient photon-based experiments that strongly addressed the detection loophole while testing Bell inequality violations with great precision. The combined message was clear. The quantum result was not a fragile accident of one particular apparatus. These experiments did not mean that every philosophical question about quantum mechanics had been answered. They did not tell physicists which interpretation of quantum theory must be emotionally satisfying before bedtime. They did, however, make the local hidden variable picture much harder to defend. The idea that entangled particles merely carried local pre-written answers from their shared past no longer matched the experimental evidence. Science then tightened the test even further. Later work used light from distant astronomical sources to help choose measurement settings. In some experiments, photons from stars in the Milky Way were used. In others, light from very distant quasars was used, coming from billions of years in the past. The purpose was to push the freedom of choice question further back in time. If the measurement settings were influenced by ancient starlight or quasar light, then any hidden coordination between the particle source and the setting choices would need to have been arranged far earlier in cosmic history. This does not prove that no possible loophole can ever be imagined. Physics is careful, and imagination is annoyingly energetic. But these cosmic Bell tests made the freedom of choice loophole far more constrained. They showed how seriously physicists took the challenge. The goal was not simply to win an argument for quantum mechanics. The goal was to ask nature the question in as many careful ways as possible, each time making the ordinary local explanation less plausible. That is the quiet beauty of this story. The first Bell tests were dramatic, but science did not stop at the drama. It kept improving detectors, it increased separations, it changed settings more quickly, it counted missed particles more carefully, it used photons, diamond defects, stars and quasars. It moved from possibility to evidence, then from evidence to stronger evidence, always tightening the net around the same strange conclusion. Entanglement is real. The correlations predicted by quantum mechanics are not a laboratory illusion easily explained by missed particles, slow settings, or ordinary hidden messages. The link that should not exist survived the careful closing of doors that might have let it escape. And with each closed loophole, the universe looked a little less like a collection of separate hidden machines, and a little more like the quantum world had been telling the truth all along. After all the experiments, after the careful closing of loopholes, after the detectors and photons and distant measurement settings, entanglement can begin to sound almost too powerful. Two particles can be separated by a great distance, measured in different places, and still show correlations that cannot be explained by ordinary local hidden variables. That sounds at first as if the universe has opened a secret channel across space. It is very tempting to imagine one particle sending a message to the other. One particle is measured here, and the other particle, far away, somehow responds. The mind reaches for familiar pictures, a signal, a pulse, a hidden flash, a tiny instruction sent across the gap. It is an understandable picture, because ordinary communication always works through some travelling influence. A voice moves through air as pressure waves. A radio transmission moves as electromagnetic radiation. A message on a phone crosses networks through signals, cables, antennas, servers, and a truly heroic amount of infrastructure that mostly goes unnoticed until the Wi-Fi fails at the worst possible moment. Entanglement is not like that. Quantum entanglement creates correlations between measurements, but it does not allow one observer to send a controlled message to another observer faster than light. This is one of the most important limits in all of quantum physics, and it is captured by the no communication theorem. In simple terms, the theorem says that entangled measurements can produce linked patterns, but the individual result seen by either observer still appears random. The pattern only becomes visible when both observers later compare their records through ordinary communication. That last part matters enormously. Imagine two people very far apart, each receiving results from measurements on entangled particles. One person measures a particle and gets a result. The other person measures the distant partner particle and gets a result too. Later, when the two lists of results are brought together and compared, the correlations can reveal the deep quantum link. But while each person is standing alone with their own results, the sequence looks random. There is no readable message inside it. There is no chosen sentence. There is no clear signal saying hello from the other side, although physics would certainly have made the textbooks more dramatic if there were. The reason is that no observer can choose the outcome of a quantum measurement in the required way. A person measuring one particle cannot decide, right, this result will be up, and therefore the faraway particle must now become down in a way that sends a meaningful signal. Quantum mechanics does not permit that kind of control. The measurement outcome is not something the observer can select like a button on a remote control. It appears probabilistic, so although the two sides are correlated, one side cannot use those correlations to encode a message. A simple comparison helps. Suppose two people each receive a long list of apparently random symbols. When one person looks at their own list, there is no obvious message. It is just a strange sequence. The other person sees the same kind of thing, but when the two lists are later placed side by side, a pattern appears between them. The relationship is real, but it was not visible from either list alone. More importantly, neither person could use their own list to control what the other person received. The pattern depends on comparison. Entanglement works with a deeper quantum structure than this simple comparison, but the communication lesson is similar. Correlation is not the same as a usable signal. This distinction keeps entanglement consistent with Albert Einstein's special relativity. Special relativity, introduced in 1905, showed that the speed of light is not merely the speed of one particular thing called light. It is the cosmic speed limit for usable information and causal influence through space-time. If messages could be sent faster than light, then cause and effect would become deeply unstable. In some frames of reference, depending on relative motion, the message could appear to arrive before it was sent. That would make reality less like a careful physical order and more like a badly edited time travel film. Quantum mechanics avoids that problem. Entanglement is genuinely non-classical. It really does produce correlations stronger than any local hidden variable theory can explain. Bell tests are not revealing a boring misunderstanding dressed in a lab coat. They are revealing something profound about the structure of quantum states. But this non-classical behavior does not let anyone send usable information faster than light. The randomness of each individual outcome protects causality in the everyday operational sense. This is why careful language is so important. It is fair to say that entanglement challenges ordinary separateness. It is fair to say that distant entangled systems can show correlations that classical local explanations cannot reproduce. It is fair to say that the quantum state of the combined system cannot always be reduced to independent descriptions of each part. It is not fair to say that entanglement is a magical telegraph. No one can use it to send a message instantly across a galaxy. No spaceship captain can use entangled particles to phone home from the far side of the Milky Way without waiting for ordinary signals. No one can build a faster-than-light internet by putting two electrons in a complicated mood and hoping for the best. Entanglement is stranger than ordinary communication, but also less useful for dramatic science fiction emergencies. This does not make it less remarkable. In some ways, it makes it more subtle. The universe seems to preserve a boundary between correlation and communication. It allows quantum systems to share a state in a way that defies classical separability, while still preventing controlled signals from outrunning light. Reality becomes stranger than classical physics, but not lawless. That balance is one of the most beautiful features of modern physics. Quantum theory and relativity appear, at first glance, to pull intuition in different directions. Quantum entanglement says that the deepest description of separated systems can be shared. Special relativity says that usable influence cannot travel faster than light. The two ideas might seem ready to quarrel across the room, yet in practice, quantum mechanics respects the no communication limit. So the link that should not exist is not a postal service. It is not a hidden wire across space. It is not a controllable whisper from one particle to another. It is a relationship written into the shared quantum state, revealed only through patterns that emerge when measurements are compared. The universe is far stranger than separate little objects carrying simple, local instruction cards. But it is not careless. It lets entangled particles be connected in a way classical physics cannot imitate, while still refusing to let anyone use that connection to break causality. Entanglement opens a door into a deeper kind of relationship, but the speed of light still stands quietly at the threshold, making sure nobody runs through with a message. Entanglement is easiest to imagine as a strange connection between particles far apart, but in the laboratory, it appears through something much more practical and less theatrical: measurement. A quantum system does not simply stand in front of a scientist and announce its secrets in a helpful little voice. Its properties are revealed through interaction. A photon meets a polarizer. An electron interacts with a detector. A measuring device becomes physically involved with the system it is measuring. The result is not just a human looking at something. It is a real event in the world, where a delicate quantum possibility becomes a recorded outcome. This is why measurement sits so close to the heart of entanglement. The strange correlations between entangled particles are not usually visible by staring at one particle alone. They are revealed when many measurements are made, recorded, and compared. Each result may look random in isolation, but the pattern between the results shows that the particles were described by one shared quantum state. The link is not a little wire across space. It is a relationship in the structure of the quantum description, made visible through careful interaction with measuring devices. But that word, interaction, is also where the difficulty begins. Quantum states are delicate. A system can be prepared in a superposition. Two systems can be entangled. Their shared state can carry the strange correlations that made Einstein uneasy and made Bell's theorem so important. But the moment that system interacts too strongly with the outside world, the measurable quantum behavior can fade into something that looks ordinary and classical. This process is called decoherence. Decoherence is the process by which a quantum system loses its clear, usable quantum behavior through uncontrolled interaction with its environment. It does not mean the system vanishes. It does not mean quantum physics stops applying. It means the delicate relationships that made superposition and entanglement observable become spread into the surrounding world in a way that makes the original quantum pattern extremely hard to recover. A simple comparison is a quiet pond. If one small ripple travels across still water, its shape can be followed. If a second ripple meets it, the two can interfere in a clear pattern. But if wind, rain, insects, falling leaves, and a moderately enthusiastic duck all disturb the surface at once, the original ripple pattern becomes lost in the wider motion. The water is still obeying physical laws, but the clean pattern has become practically inaccessible. Decoherence is not exactly the same, but the comparison captures the feeling. The fragile pattern becomes dispersed into too many surrounding details. The physicist Heinz Dieter Zeh was one of the important early figures in the study of decoherence. In the 1970s, he argued that interaction with the environment plays a crucial role in explaining why quantum superpositions are not seen directly in ordinary macroscopic objects. Later, Wojciech Zurek developed this idea further, especially through the study of how classical-looking reality emerges from quantum systems interacting with their environments. Zurek also worked on ideas such as environment-induced superselection, where certain stable states are effectively selected by the environment because they survive interaction better than more delicate alternatives. This helps explain a great puzzle. If quantum mechanics is the underlying theory of matter, and if everything is made from quantum systems, why does the world not look wildly quantum all the time? Why do tables not sit in obvious superpositions of here and slightly over there? Why do cups of tea not visibly behave like entangled laboratory systems, apart from the mysterious way they cool down exactly when forgotten? Why do people, chairs, planets, and books appear so solidly classical? Decoherence is a major part of the answer. Large objects are not isolated. They're constantly interacting with their surroundings. Air molecules bounce from their surfaces. Photons of light scatter from them. Heat flows through them. Vibrations pass through them. Electromagnetic fields disturb them. Every moment, information about their position and condition leaks into the environment. A table is not quietly preserving one pristine quantum state, like a precious snowflake inside a vacuum chamber. It is being touched, warmed, illuminated, and bumped by countless particles and fields. Its quantum subtleties are washed into the world around it almost immediately. This does not mean entanglement is rare in principle. In fact, it is almost the opposite. Quantum systems can become entangled whenever they interact in the right way. The universe is constantly producing complicated quantum relationships. The challenge is not that entanglement never happens. The challenge is producing the right kind of entanglement, keeping control of it, and stopping it from being ruined by unwanted contact with the environment. This is why laboratories that study quantum information can look so carefully protected. Quantum systems may need extreme cold, sometimes temperatures close to absolute zero. They may need high vacuum chambers to remove air molecules. They may need shielding from stray electromagnetic fields. They may need isolation from vibration so tiny disturbances do not scramble the state. They may need carefully timed lasers, precise electronics, and detectors sensitive enough to register single particles. The universe is generous with quantum behavior, but not always tidy about handing it over in a useful form. Heat is especially troublesome because temperature is connected to motion and energy spread among many particles. A warm environment is busy. Atoms vibrate. Molecules collide. Electromagnetic radiation is exchanged. For fragile quantum states, this bustle can act like background noise, quickly entangling the system with countless uncontrolled degrees of freedom. Once that happens, the clean entanglement that scientists wanted to measure or use may become buried inside a much larger, messier quantum state. This is the practical side of the mystery. Entanglement is powerful, but it is not convenient. It does not sit politely on a shelf waiting to be used. It must be prepared, protected, manipulated, and measured before the surrounding world interferes too much. Modern quantum technology depends on this careful control. Quantum computers, quantum sensors, and quantum communication experiments are not built simply by admiring the strangeness of entanglement from a safe distance. They are built by fighting, very gently and very precisely, against decoherence. So the ordinary world looks classical not because quantum physics disappears, but because uncontrolled interaction makes delicate quantum behavior extremely difficult to see at large scales. Measurement reveals entanglement, but measurement is also one example of the broader truth that interaction changes how quantum possibilities become recorded facts. The link that should not exist is real, but it is fragile. It can survive across distance under the right conditions, yet it can be blurred by a warm laboratory bench, a stray field, a vibration, or a single careless interaction with the surrounding world. Entanglement shows that nature is deeper than ordinary separateness, but decoherence explains why that depth is usually hidden beneath the calm, solid appearance of everyday things. Once entanglement is protected from the noise of the surrounding world, it stops being only a strange fact about measurement and becomes something more practical. it becomes a resource. Carefully prepared, carefully shielded, and carefully measured, entanglement can be used to move quantum information in a way that has no classical equivalent. This is where quantum teleportation enters the story, and the name is both wonderful and slightly dangerous. Quantum teleportation does not mean that a person disappears from one place and reappears somewhere else. It does not mean a spaceship vanishes in a flash of light. It does not even mean that a particle's physical body is picked up and transported across space, like a tiny parcel, with excellent tracking information. No atoms are dematerialized. No nervous scientist is accidentally duplicated. No one has to worry about stepping into a machine and wondering whether the version that steps out is really them, which is a comforting limit for both physics and customer service. Quantum teleportation means the transfer of an unknown quantum state from one system to another, using entanglement and ordinary classical communication. The state is the key word. What is being transferred is not the material object itself, but the quantum information describing the state of a system. This idea was proposed in 1993 by Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters. Their work showed that entanglement could be used in a precise information task. The same phenomenon that had troubled Einstein, sharpened the Einstein, Podolsky, and Rosen debate, and inspired Bell's theorem could also become part of a practical protocol. The basic ingredients are surprisingly elegant. First, two systems are prepared in an entangled state. One part of this entangled pair is kept by the sender, and the other part is sent to the receiver. Then the sender also has a third system, whose unknown quantum state is the one to be teleported. The sender performs a special joint measurement on the unknown state, and on their half of the entangled pair. This measurement changes what can be known and used, and it produces a result that must be sent to the receiver through ordinary classical communication. That classical message is essential. Without it, the receiver cannot reconstruct the intended quantum state. This is why quantum teleportation does not allow faster-than-light communication. Even though entanglement is involved, the receiver still needs the sender's ordinary message before the process can be completed. The speed of light remains very much employed, standing there quietly with a clipboard, making sure causality does not wander off. Once the receiver gets the classical information, they can perform the correct operation on their half of the entangled pair. The result is that their system takes on the original quantum state. The state has effectively been transferred from one system to another. But there is a subtle and important limit. The original quantum state is not copied. Quantum mechanics includes a principle called the no-cloning theorem. It says that an unknown quantum state cannot be perfectly copied in a general way. This is not just a problem of bad machinery or insufficiently enthusiastic engineering. It is built into the structure of quantum theory. Unlike ordinary information, such as a written sentence or a digital file, an unknown quantum state cannot simply be duplicated while leaving the original untouched. So in quantum teleportation, the original state is destroyed by the measurement process as the state is transferred. This is what keeps the protocol consistent with quantum rules. It is not making a spare copy. It is not photocopying reality and hoping nobody notices. The information is relocated, not duplicated. This makes quantum teleportation very different from science fiction teleportation. In fiction, teleportation usually means moving matter itself from one location to another. A person or object is scanned, disassembled, transmitted and reconstructed, often with just enough dramatic humming to suggest that something very expensive is happening. Quantum teleportation is much narrower. It is about moving a quantum state between systems. That might sound less glamorous, but scientifically it is extraordinary. It means entanglement can function as a channel for quantum information, provided the rules are obeyed. The entangled pair supplies a shared quantum resource. The measurement links the unknown state to that resource. The classical message tells the receiver how to complete the reconstruction. Remove any one of those pieces and the process fails. Anton Zeilinger's research group played an important role in turning quantum teleportation from a theoretical protocol into an experimental reality. In the late 1990s, Zeilinger and colleagues demonstrated teleportation of quantum states using photons. Later experiments extended the idea across different physical systems and greater distances, including work with trapped ions, atoms, solid-state systems, optical fibers, and satellite-based quantum communication. Each demonstration faced the same general challenge: create entanglement, preserve it long enough, perform precise measurements, and keep ordinary environmental disturbance from washing away the fragile quantum information. This connects directly to the fragility of quantum states. Teleportation is not possible just because entanglement exists somewhere in principle. It requires controlled entanglement. The particles or systems involved must be prepared with care, isolated from unwanted interactions, and measured with enough precision that the quantum correlations remain useful. Heat, vibration, stray electromagnetic fields, and imperfect detectors can all degrade the process. The link that should not exist must be treated less like a magic tunnel and more like a very delicate scientific instrument. Quantum teleportation also reveals something profound about what quantum information means. In everyday life, information can often be separated from its physical carrier quite easily. A sentence can be written on paper, typed on a screen, spoken aloud, or stored digitally. The same message can have many copies. Quantum information is more restrictive. It belongs to the state of a physical system, and the rules for handling it are deeply shaped by measurement, superposition, entanglement, and the no-cloning theorem. That is why teleportation is such a powerful example. It shows that entanglement is not just a strange correlation discovered after the fact. It can be used, but only on quantum terms. It does not give permission to break relativity. It does not allow unlimited copying. It does not move matter like a science fiction machine. Instead, it moves an unknown quantum state through a carefully choreographed combination of shared entanglement, measurement, and ordinary communication. The result is quieter than fiction, but in some ways more beautiful. A quantum state can disappear from one system and appear in another, not by travelling as a little object through the space between them, but by using a relationship prepared in advance and completed with a classical message. Entanglement becomes a tool, but never a loophole for everything. It is powerful because it is precise, and strange because it obeys rules that ordinary common sense would never have guessed. Quantum teleportation shows that entanglement can move quantum information from one system to another, but only when the rules are followed with great care. It cannot send a message faster than light. It cannot make a copy of an unknown quantum state. It cannot rescue a spaceship from the far side of the galaxy, though science fiction may continue filing polite complaints. What it does show is that entanglement can be used as a resource, not just admired as a mystery. That same shift appears in quantum cryptography. Cryptography is the science of protecting information. In ordinary digital life, it is everywhere. It helps secure bank transfers, private messages, passwords, online shopping, medical records, and countless other quiet exchanges that depend on information reaching the right person without being read by the wrong one. Most modern cryptography relies on mathematical problems that are easy to use in one direction but extremely difficult to reverse without the right key. Quantum cryptography approaches the problem differently. It uses the physical rules of quantum mechanics to help detect eavesdropping and distribute secret keys more securely. The most important idea is quantum key distribution. A key is a shared string of information that two parties can later use to encrypt and decrypt messages. The message itself may still travel through ordinary channels, but the key is created in a way that uses quantum behavior to reveal whether someone has tried to interfere. The key point is measurement disturbance. In quantum mechanics, measuring a system is not always a passive act, like glancing at a signpost or checking whether the kettle has boiled. Measurement can change the system being measured. If information is encoded in quantum states, An eavesdropper cannot simply peek at it without risk. The attempt to measure those states can disturb them, introducing detectable errors. In a properly designed quantum key distribution system, the legitimate users can compare part of their data and estimate whether the transmission has been disturbed. If the error rate is too high, they know the key may not be secure and can reject it. This is not quite a spy thriller. There does not need to be a villain in a black coat leaning over a glowing console while whispering, "Enhance the photon." The science is quieter than that. It is about statistics, measurement settings, error rates, and the physical impossibility of extracting certain quantum information without leaving traces. The drama is not in chase scenes. It is in the fact that the rules of nature themselves can help reveal unwanted observation. In 1984, Charles Bennett and Gilles Brassard proposed one of the foundational quantum key distribution protocols. Their idea used non-orthogonal quantum states, meaning quantum states that cannot be perfectly distinguished from each other by measurement. This made eavesdropping detectable, because any attempt to intercept and measure the transmitted quantum systems would introduce errors into the shared data. It was a practical use of the same quantum strangeness that had once seemed mainly philosophical. Then, in 1991, Arthur Eckert proposed an entanglement-based approach to quantum key distribution. In this version, entangled particles are shared between two distant users. By measuring their particles and checking the correlations between the results, the users can test whether the shared correlations behave in a genuinely quantum way. Bell inequality tests can become part of the security logic. If the correlations are strong enough in the right quantum sense, then they can help show that the key is not simply being produced by a classical hidden mechanism that an eavesdropper might secretly know. This is where entanglement becomes especially powerful. It does not merely make two measurement records look interesting after the fact. It can help establish whether the shared information has a distinctly quantum origin. The strange link that once troubled Einstein becomes a tool for checking trust. Nature, in a sense, is asked not only whether the particles are connected, but whether that connection is strong enough to rule out certain kinds of classical imitation. But quantum cryptography should not be oversold. It does not magically make every computer system secure. Real devices are physical machines, and physical machines have imperfections. Detectors may behave differently from the ideal theory. Light sources may produce unwanted signals. Software may contain bugs. Hardware may leak information through side channels. People may use weak passwords, misconfigure systems, click suspicious links, or write important secrets on sticky notes with the serene confidence of someone inviting chaos to tea. The theory can be extremely strong, but the implementation still matters. A quantum key distribution system is only as secure as the devices, assumptions, engineering, and procedures that support it. This is an important balance. Quantum cryptography is not magic dust sprinkled over a network. It is a serious technology built on deep physics, and like all serious technologies, it must survive contact with the real world. Still, the achievements are remarkable. Quantum communication has been tested through optical fibers, across free space, and over increasingly long distances. One major milestone came with satellite-based quantum communication. In 2016, China launched the Mikyus satellite, named after the ancient Chinese philosopher Mozi. This satellite was used in experiments involving quantum key distribution and entanglement over very large distances, including tests between ground stations separated by more than 1,000 kilometers. The work showed that quantum communication is not restricted to small laboratory benches. Under the right conditions, entangled photons and quantum keys can be handled across distances that begin to feel planetary. This matters because ordinary optical fibers absorb photons over distance, and quantum signals cannot simply be copied and boosted in the usual way because of the no-cloning theorem. Satellites offer one possible route around that difficulty, by sending photons through space, where losses can be lower than through long stretches of fiber. Even then, The engineering is demanding. The photons must be generated, transmitted, pointed, detected, and analysed with extraordinary precision. The universe may allow entanglement, but it does not automatically fill in the paperwork. The deeper lesson is that entanglement has moved from paradox to technology. It began as a challenge to ordinary ideas about separateness, locality, and measurement. It troubled Einstein, inspired Bell, and forced experiments to confront the question of what nature actually permits. Now it also helps shape practical tools for communication and security. Quantum cryptography shows that the link that should not exist is not only a philosophical puzzle, it is a physical resource. It cannot do everything. It cannot remove every weakness from human technology, and it cannot turn secrecy into something effortless. But it can handle information in ways classical physics cannot fully imitate, using the fragile, measurable, and surprisingly useful strangeness of the quantum world. Quantum communication shows that entanglement can help protect and move information in ways classical physics cannot fully copy. But there is another place where the same strange link becomes even more ambitious. Instead of using entanglement only to share keys, test security, or transfer a quantum state, physicists and engineers are trying to use it as part of a new kind of computation. A quantum computer is not simply a very fast ordinary computer. It is a device that uses quantum systems to store and process information. An ordinary classical computer uses bits. A bit has one of two possible values, usually described as 0 or 1. Every photo, message, video calculation, and mildly suspicious spreadsheet ultimately becomes a long pattern of these classical bits. They are simple, dependable, and astonishingly powerful when arranged in great numbers. A quantum computer uses quantum bits, usually called qubits. A qubit can be built from many possible physical systems, such as the energy levels of an atom, the spin of an electron, the polarization of a photon, the state of a superconducting circuit, or the internal states of trapped ions. The important point is not that a qubit is smaller or somehow more glamorous than a bit, though it does sound like something that should come with a tiny velvet rope. The important point is that a qubit obeys quantum rules. A qubit can exist in superposition, meaning its state can be described as a combination of possible measurement outcomes before a measurement is made. When several qubits are brought together, they can also become entangled. This means the state of the whole group may no longer be reducible to a neat list of separate states for each qubit. The system has a shared quantum description, just as entangled particles do in the experiments inspired by Einstein, Podolsky, Rosen, and Bell. This is one of the reasons quantum computers are so interesting. Entanglement can allow quantum computers to represent certain patterns of information in a way that has no ordinary classical equivalent. A group of entangled qubits is not merely a pile of independent switches. The correlations between them can become part of the information being processed. In carefully designed calculations, quantum gates manipulate these states. Quantum interference strengthens some possible answers, and measurement extracts a final result. The idea that quantum systems might be best studied with quantum machines was strongly associated with Richard Feynman. In the early 1980s, Feynman argued that simulating quantum physics on ordinary classical computers becomes extremely difficult because the amount of information needed to describe quantum systems can grow enormously as more particles are included. His insight was wonderfully direct. If nature is quantum, perhaps a computer built from quantum systems would be a more natural tool for studying it. David Deutsch later developed the concept of a universal quantum computer. This helped turn the idea into a broader theoretical framework, showing that quantum computation was not just a special trick for one kind of simulation. It could be understood as a general model of computation, with its own logic, operations, and possibilities. For a while, quantum computers were mostly a beautiful theoretical idea. Then certain algorithms revealed why they might matter far beyond curiosity. In 1994, Peter Shaw discovered a quantum algorithm that could factor large numbers much more efficiently than the best-known classical methods. This was important because some widely used cryptographic systems rely on the difficulty of factoring large numbers. Shaw's algorithm showed that a sufficiently powerful quantum computer could threaten certain kinds of classical encryption. Then Love Grover developed a quantum search algorithm in 1996. Grover's algorithm showed that a quantum computer could search an unstructured list with fewer steps than a classical computer would need. It did not make every hard problem instantly easy, but it showed another clear way that quantum computation could offer a different kind of advantage. Still, entanglement is not the whole story. A common mistake is to imagine that entanglement alone is the magic ingredient that makes quantum computers powerful. It is important, but it is not sufficient by itself. Quantum computation also depends on superposition, interference, quantum gates, measurement, error correction, and the physical design of the machine. Entanglement may help create correlations and shared states that classical systems cannot simply imitate, but the calculation only works when the entire quantum process is controlled with great precision. This is where the dream becomes difficult. Qubits are fragile. They are disturbed by the same kinds of environmental contact that make entanglement hard to preserve elsewhere. Heat can jostle the system. Stray electromagnetic fields can shift delicate states. Vibrations can disturb trapped particles or laboratory equipment. Imperfect materials can introduce noise. Even the act of controlling a qubit with lasers, microwaves, or electrical pulses can introduce errors if it is not done carefully enough. To perform useful computations, qubits must remain coherent long enough for operations to be carried out. Coherence means that the quantum relationships needed for the computation, including superposition and entanglement, remain usable rather than being washed away by decoherence. This is one of the central practical challenges of the field. A quantum computer must be open enough to control and measure, but isolated enough to protect its fragile state. It is a little like trying to play a violin during a thunderstorm while wearing oven gloves, except the violin is an atom, and the thunderstorm is the rest of the universe. This is why quantum error correction is so important. Ordinary computers use error correction too, but quantum error correction must respect the rules of quantum mechanics, including the no-cloning theorem. Unknown quantum states cannot simply be copied and backed up in the usual way. Instead, information is distributed across entangled groups of qubits so that certain errors can be detected and corrected without directly measuring and destroying the quantum information being protected. Organizations such as the National Institute of Standards and Technology, Google Quantum Artificial Intelligence, International Business Machines, IonQ, and many academic laboratories around the world are working on different approaches to quantum hardware. Some use superconducting circuits cooled to temperatures close to absolute zero. Others use trapped ions held in electromagnetic fields and controlled with lasers. Others explore photons, neutral atoms, defects in diamond, or other physical platforms. Each approach has strengths and weaknesses, and none has yet made quantum computers simple, cheap, or casually available beside the printer, which is probably just as well given what printers are already like. The deeper point is that entanglement has travelled a long way in the story of physics. It began as a troubling feature of quantum theory, something that made Einstein worry that the theory might be incomplete. Bell turned it into a test. Experiments showed that the strange correlations were real. Quantum communication then showed that entanglement could help handle information in ways classical physics cannot fully reproduce. Inside quantum computers, that same strange link becomes part of a larger machine for processing possibilities. It is not magic, and it does not make every calculation faster. But under the right conditions, entanglement helps quantum systems carry and transform information in patterns that ordinary bits cannot naturally hold. The link that should not exist has become one of the building blocks of modern quantum technology, fragile, demanding, and quietly astonishing. Quantum computers make entanglement feel like something carefully engineered, protected inside cold machines, held in qubits shaped by gates, and guarded from the noisy world outside. But entanglement is not only something researchers create in devices, it is also something nature already uses, quietly and constantly, inside matter itself. The story begins to widen beyond pairs of particles. A pair of entangled photons is strange enough. Two distant measurements, one shared quantum state, and correlation stronger than classical separateness allows. But real materials are not usually made of two particles politely waiting to be measured. They are made of enormous numbers of interacting particles. A grain of salt, a sliver of metal, a magnet, a crystal, or a superconducting wire contains vast crowds of electrons, atomic nuclei, vibrations, fields, and forces, all behaving together in ways that cannot always be understood by treating each particle as if it were alone. This is the world of many-body physics. Many-body physics is the study of systems made from large numbers of interacting particles. It asks how simple microscopic rules can produce complex collective behavior. Electrons moving through solids, atoms chilled into ultra-cold gases, spins arranged in magnetic materials, and quantum particles trapped in artificial lattices can all belong to this field. The central question is not only what one particle does, but what many particles do together when every one of them is influenced by the others. This matters because matter has phases. Water can be solid ice, liquid water, or vapor. Iron can become magnetized. Some materials become superconductors. Others behave as insulators, metals, semiconductors, or more exotic quantum states. A phase of matter is not just a list of individual particle behaviors. It is a collective pattern. The particles form a shared order, and in quantum systems, entanglement can be part of what makes that order possible. In ordinary classical thinking, the temptation is to describe every particle separately, then add the pieces together. Sometimes that works well enough, but in many quantum materials, the whole cannot be understood as a simple crowd of independent particles. Electrons are indistinguishable quantum objects. Their wave functions can overlap. Their spins, charges, and allowed states are shaped by the Pauli exclusion principle, electromagnetic interactions, and the surrounding structure of the material. In strongly quantum systems, correlations between particles can become so important that the individual particle picture becomes too thin. Superconductivity is one of the most famous examples. In a superconductor, electrical current can flow with zero electrical resistance under the right conditions. That means a current can persist without the usual energy loss as heat. This is not how ordinary metal behaves. In a normal wire, moving electrons scatter from vibrations in the crystal lattice, impurities, and other disturbances. Resistance appears and energy is lost. A superconductor does something stranger. In 1957, John Bardeen, Leon Cooper, and John Robert Schrieffer developed the theory that explained conventional superconductivity. In their theory, electrons inside a material can form correlated pairs, now called Cooper pairs. These pairs are not simply two tiny balls stuck together. They are quantum correlations spread through the material, helped by interactions with vibrations of the atomic lattice called phonons. Many Cooper pairs then join into a collective quantum state, allowing current to move through the material without ordinary resistance. The key idea is collective behavior. One electron alone does not make a superconductor. A whole sea of correlated electrons does. The superconducting state is described by a shared quantum order that extends across the material. Entanglement and quantum correlation help explain why the state cannot be reduced to a simple picture of separate electrons drifting independently through a wire. Quantum magnetism gives another window into the same theme. Magnetism depends on spin, the intrinsic quantum property associated with angular momentum and magnetic behavior. In a simple picture, tiny spins line up like little compass needles. That can be useful as a first image, But real quantum magnets can be much more subtle. Spins can interact with neighbouring spins, forming collective states that may be ordered, disordered, frustrated, or deeply entangled. In some materials, the geometry of the lattice prevents every spin interaction from being satisfied at once. This can produce quantum frustration, where the system cannot settle into one simple arrangement. Spin chains are a particularly clear example. In a spin chain, quantum spins are arranged in a line and interact with their neighbours. Even though the system sounds simple, its behaviour can be surprisingly rich. The ground state, meaning the lowest energy state, may involve entanglement spread along the chain. Measuring or describing one spin alone may miss the important structure, because the physics lives in the relationships among the spins. The material is not just a set of isolated little arrows, it is a shared quantum pattern. This is where entanglement becomes more than a curiosity. In many body systems, it helps physicists classify and understand phases of matter. Some phases look ordinary, with local order that can be described through familiar quantities. Others are more exotic, including topological phases, where important properties are not tied to one location, but to the global structure of the quantum state. In these cases, entanglement can reveal hidden order that would be difficult or impossible to see by inspecting particles one by one. The difficulty is that many body quantum systems are extremely hard to calculate. The full mathematical description can grow explosively as more particles are added. A few qubits or spins may be manageable. A large material with countless interacting particles quickly becomes overwhelming. This is one reason quantum computers are so interesting, but even before useful large quantum computers arrive, physicists have built clever mathematical tools. Tensor networks are one of those tools. They describe complicated quantum states by focusing on patterns of entanglement. Instead of trying to store every possible detail in one enormous object, tensor network methods use structure in the entanglement to make the problem more manageable. Stephen White's density matrix renormalization group, introduced in the early 1990s, became one of the most powerful methods for studying one-dimensional quantum systems, especially spin chains and strongly correlated electrons. It works so well partly because many important low-energy states have entanglement patterns that can be represented efficiently. The lesson is beautifully quiet. Entanglement is not only a laboratory trick, a philosophical headache, or a resource inside future machines. It is woven into the behaviour of matter. It helps explain how electrons move together, how magnets form collective states, how superconductors carry current without resistance, and how complex phases emerge from simple quantum rules. The link that should not exist is not confined to two distant particles. Inside matter, it becomes a many-voiced relationship, spread across particles that cannot always be understood alone. Nature was using entanglement long before anyone tried to build a quantum computer. Physics simply learned how to notice. Entanglement has already moved through photons, detectors, secure keys, quantum computers, and the hidden collective behaviour of matter. It has appeared in places that feel almost practical. Laboratory benches, optical fibres, superconducting circuits, trapped ions, and magnetic materials. But the same idea also reaches into some of the deepest questions in physics, where the subject becomes quieter, stranger, and less settled. At the edge of modern theory, entanglement begins to touch gravity, space-time, and black holes. That may sound like a sudden leap. A pair of entangled photons in a laboratory seems very different from a black hole bending space-time with such intensity that not even light can escape. Yet both belong to the unfinished attempt to understand how quantum mechanics and gravity fit together. Quantum mechanics is the theory of atoms, particles, fields, measurement, and information. General relativity as Albert Einstein's theory of gravity both belong to the unfinished attempt to understand how quantum mechanics and gravity fit together. Quantum mechanics is the theory of atoms, where mass and energy shape space-time itself. Each theory works extraordinarily well in its own domain. The trouble begins in places where both should matter at once. Black holes are one of those places. A black hole forms when matter becomes compressed so intensely that a boundary called an event horizon appears. Beyond that boundary, escape becomes impossible for anything travelling at or below the speed of a light. In classical general relativity, the event horizon is not a solid surface. It is a point of no return in space-time. But when quantum theory enters the story, black holes become more mysterious. In the 1970s, Stephen Hawking showed that black holes should not be perfectly black. Quantum field theory near the event horizon suggests that black holes can emit radiation, now called Hawking radiation. Over immense timescales, this means a black hole can lose energy and eventually evaporate. For a black hole with the mass of the Sun, this process would take vastly longer than the current age of the universe, so there is no need to worry about nearby stellar black holes politely steaming away before breakfast. The problem is information. In quantum mechanics, information is expected to be preserved. This does not mean information is always easy to recover, or neatly filed in a sensible folder. It means that the complete quantum state should evolve in a way that does not simply erase information from existence. But Hawking's original calculations seem to suggest that black hole evaporation might produce radiation that carries away energy while losing detailed information about what fell in. If a black hole forms from matter in a particular state, then evaporates into featureless radiation, where did the original information go? This became known as the black hole information problem. Jacob Bekenstein had already taken a crucial step by arguing that black holes have entropy. Entropy is a measure connected to the number of possible microscopic arrangements compatible with a system's overall state. Bekenstein proposed that a black hole's entropy is related not to its volume, but to the area of its event horizon. Hawking radiation then tied black holes even more deeply to thermodynamics and quantum theory. Together, Bekenstein and Hawking showed that black holes are not merely gravitational traps, they're also physical systems with temperature, entropy, and quantum behaviour. This was a remarkable clue. In ordinary systems, entropy usually grows with volume. A box of gas has more possible internal arrangements if the box is larger, but black hole entropy scales with the area of the horizon. That strange fact helped inspire the holographic principle. Gerard 't Hooft and Leonard Susskind developed the idea that the information contained in a region of space may be deeply related to the boundary surrounding that region. The name comes from a hologram, where a two-dimensional surface can encode information about a three-dimensional image. It is not saying the universe is literally a sticker on a cosmic window. It is saying that gravity and information may be connected in a much deeper way than everyday intuition suggests. Juan Maldacena gave this idea a powerful mathematical form in 1997 through the anti-de Sitter and conformal field theory correspondence. This framework relates a theory of gravity in a certain kind of space-time to a quantum field theory on its boundary. It has become one of the most important tools in theoretical physics, especially for studying quantum gravity, black holes, and strongly interacting quantum systems. It must be handled carefully. The anti-de Sitter and conformal field theory correspondence does not simply describe our universe in a finished, direct, everyday way. Our universe appears to have a different large-scale structure from anti-de Sitter spacetime. But as a theoretical laboratory, Maldacena's framework is extraordinary. It shows that spacetime geometry and quantum information can be mathematically linked with surprising depth. Entanglement enters here in a profound way. In many versions of the holographic idea, entanglement is not just another feature inside spacetime. It may help explain how aspects of spacetime geometry are built. Some research suggests that the pattern of entanglement in an underlying quantum theory is related to the shape, connectivity, or emergence of spacetime in the gravitational description. This does not mean physicists have fully solved quantum gravity. The subject remains active, difficult, and unfinished, but it does mean entanglement may be part of the language needed to understand why spacetime has the structure it does. This connects gently back to many body physics. In a complex material, entanglement can organize the behavior of many particles into faces that cannot be understood by separating each particle from the others. In quantum gravity, some physicists suspect a deeper version of the same lesson may apply. The geometry of space may not be a simple background stage on which quantum systems perform. It may, in some circumstances, be connected to the entanglement structure of the quantum world itself. The idea is still developing. It should not be inflated into certainty. No complete experimentally confirmed theory of quantum gravity currently explains everything. But the direction is striking. Entanglement began as an awkward feature of quantum measurement. It became a test of local realism. It became a tool for communication and computation. Then, at the frontier, it became a possible clue to the nature of space-time, black holes, and information itself. The link that should not exist may reach further than two particles. It may run through matter, through technology, through horizons, and into the unfinished question of how space and gravity emerge from quantum law. At this edge of understanding, physics does not yet offer a final answer. It offers something quieter and perhaps more interesting. Evidence that the separateness of things may not be the deepest layer of reality. After travelling through black holes, holographic ideas, quantum computers, secure communication, teleportation, and the delicate experiments that tested Bell's theorem, it is worth returning to solid ground for a moment. Entanglement is real, but real things can still be misunderstood. In fact, entanglement may be one of the most misunderstood ideas in modern science. It has all the ingredients that make an idea easy to stretch too far. It is strange. It is mathematically deep. It involves distant systems. It troubled Einstein. It has been tested in experiments. It uses words like measurement, information, and connection, which already sound as if they're quietly opening a side door into mystery. Add a few dramatic headlines, and suddenly entanglement can be made to look like almost anything. But good science needs boundaries as much as wonder. Quantum entanglement does not prove telepathy. It does not show that thoughts can be sent instantly from one mind to another. It does not mean two people can become quantum linked by staring meaningfully across a room, even if the room has candles and a suspicious amount of ambient music. It does not prove mystical consciousness. It does not mean every object in the universe is connected in a practical everyday sense that can be used, controlled, felt, or turned into a message. The real idea is already strange enough without needing extra fog poured over it. Entanglement is a measurable quantum relationship between systems. When two or more quantum systems are entangled, the full quantum state describes the combined system in a way that cannot be reduced to fully independent descriptions of each part. When measurements are made, the results can show correlations stronger than local hidden variable theories allow. That is the core scientific claim. It is powerful, precise, and experimentally supported. The meaning must stay tied to measurable quantum correlations. This point protects the mystery rather than reducing it. The real mystery of entanglement is not that it lets anyone do whatever sounds dramatic. The real mystery is that nature violates the simple expectation that distant objects must always carry their own complete local properties, waiting to be revealed. Bell tests have shown that the pattern of results does not fit the old picture of particles simply carrying hidden instruction cards from their shared past, at least not if those hidden instructions obey locality. That is extraordinary. It does not need to become telepathy to matter. The other vital boundary is communication. Entanglement does not allow someone to control another particle's measurement result across distance. If one observer measures one particle from an entangled pair, the result cannot be chosen at will. The outcome appears random to that observer. The distant observer also sees a result that appears random on its own. Only when both sets of results are later compared through ordinary communication does the deeper pattern become visible. This is why entanglement does not let information bypass the speed of light. Albert Einstein's special relativity places a strict limit on usable signals and causal influence. information cannot be sent faster than light in ordinary space-time without creating severe problems for cause and effect. Quantum entanglement respects that operational limit. It challenges classical separability, but it does not become a faster-than-light telephone. The universe is strange, but it has not casually invented a cosmic messaging app and forgotten to mention it to engineers. The difference between correlation and control is essential. A correlation means that two sets of results are related in a pattern. Control means one side can choose an outcome and use it to send a meaningful message to the other side. Entanglement gives the first, not the second. Without control, there is no message. Without a message, there is no faster-than-light communication. This is also why phrases such as "everything's connected" need care. At a very broad level, the universe does contain deep relationships. Particles interact. Fields extend through space. Matter has common origins in cosmic history. Quantum systems can become entangled through interaction, but it does not follow that every object remains usefully entangled with every other object in a clean, controllable, meaningful way. Decoherence spreads delicate quantum relationships into the environment so quickly that ordinary large objects behave classically for all practical purposes. A cup of tea may be made of quantum matter, but it is not offering a usable Bell test every time it cools beside the sofa. Entanglement must also be separated from interpretations of quantum mechanics. The experimental facts are one thing, the meaning of those facts is another. The Copenhagen interpretation, associated with Niels Bohr and others, emphasizes measurement arrangements, observed outcomes, and the limits of applying classical descriptions to quantum systems before measurement. In this view, quantum theory gives rules for what can be said about experimental results, and entanglement is part of that framework. The many worlds interpretation associated with Hugh Everett treats the wave function as always evolving smoothly, with measurement leading to branching outcomes rather than a single collapse. Entanglement becomes deeply connected to how different branches of the quantum state stop interfering with one another in ordinary experience. Pilot wave theory, developed in its modern form by David Bohm, keeps definite particle positions guided by a wave-like structure. It can reproduce many predictions of standard quantum mechanics, but it is explicitly non-local. It does not restore the simple classical dream of local separateness. Objective collapse models propose that wave function collapse is a real physical process, not merely an update of knowledge. These models try to modify quantum mechanics so that definite outcomes arise through a genuine mechanism, often becoming more important for larger systems. Relational quantum mechanics, associated with Carlo Rovelli, suggests that quantum states are not absolute descriptions from nowhere, but descriptions relative to interactions between physical systems. In this view, the properties of systems are tied to relations, not to detached, universal property lists. These interpretations differ deeply. They offer different pictures of what the mathematics is saying about reality. Yet all successful interpretations must preserve the experimental facts. They must agree with the observed violations of Bell inequalities. They must agree that entanglement produces non-classical correlations. They must agree that these correlations do not allow controlled faster-than-light signaling. Physicists can disagree about what the quantum state ultimately means, while still agreeing strongly on what experiments predict and measure. That is a useful kind of humility. It allows room for philosophical depth without confusing speculation with evidence. Entanglement is beautiful because it is real and restrained. It does not say less than the experiments show, but it also should not be made to say more. It tells that separateness is not as simple as classical physics once assumed. It tells that the whole can sometimes have a quantum state that cannot be broken into independent parts. It tells that measurement outcomes can be correlated in ways no local hidden variable theory can reproduce. It does not tell that minds communicate instantly, that consciousness controls particles, or that the universe is secretly sending personal messages through every coincidence. The louder myths tend to gather around entanglement like slightly over-enthusiastic fog. They make the idea look larger from a distance but less clear up close. The real science is sharper, quieter, and far more interesting. Entanglement is not magic pretending to be physics. It is physics revealing that reality itself is less separable, less intuitive, and more relational than everyday experience suggests. The link that should not exist does exist, but it exists as a precise quantum relationship, not as a blank check for every mystery the human imagination would like to attach to it. Its beauty lies in that balance, strange enough to unsettle classical common sense, disciplined enough to be tested, and limited enough to keep cause and effect intact. Entanglement feels like the link that should not exist, because everyday intuition expects reality to be built from separately complete things. That expectation is not foolish. It works beautifully in the ordinary world. A stone has a position, a cup has a temperature, a planet has an orbit. A book on a table does not seem to need a shared hidden description with another book across the room before either of them can be understood. Objects appear to carry their own properties with them, like quiet little biographies written into matter. They may interact, collide, attract, warm, cool, scatter light, or exchange forces, but they still seem to be separate things first and related things second. Classical physics gave that intuition a grand and powerful form. Isaac Newton's laws of motion and universal gravitation described a world of objects, forces, positions, velocities, and predictable change. Locality added another reassuring principle. Physical influence should not simply appear across distance without travelling through the space between. A ripple crosses water. Light crosses space. A radio signal takes time. A gravitational change in Albert Einstein's general relativity travels at the speed of light. Cause and effect seemed to have a geography. Then quantum physics began to loosen that picture. Max Planck's work on blackbody radiation in 1900 suggested that energy could be exchanged in discrete packets. Einstein's explanation of the photoelectric effect in 1905 showed that light, already understood as a wave, could behave as if it came in particle-like photons. Niels Bohr's atomic model in 1913 introduced allowed energy levels inside atoms, helping explain why ordinary matter does not collapse. Louis de Broglie then proposed that matter itself could have wave-like properties, and experiments later supported the strange idea that electrons could diffract like waves. The world had not stopped being orderly. It had stopped being simple. The wave function gave quantum theory its new language. Erwin Schrödinger's wave mechanics and Werner Heisenberg's matrix mechanics offered different mathematical routes into the same quantum landscape. Max Born's probability interpretation made the situation even stranger by explaining that the wave function gives probabilities for measurement outcomes. It was not merely a blurry picture caused by poor eyesight or clumsy instruments. Quantum probability appeared to be part of how measurable outcomes emerge. Superposition then showed that a quantum system can be described as a combination of possible outcomes before measurement. This did not mean the universe had become vague or sloppy. Quantum mechanics remained precise. But the precision was not always the precision of pre-existing properties, waiting calmly to be uncovered. It was the precision of probabilities, amplitudes, interactions, and outcomes. Entanglement takes that shift one step deeper. When two or more quantum systems are entangled, the complete description belongs to the combined system in a way that cannot be fully reduced to independent descriptions of each part. The whole is not merely a collection of separate property lists. The relationship is not an afterthought added between finished objects. In the quantum description, the shared state can be fundamental. That is why the phrase feels so unsettling. The link should not exist only if reality must always be assembled from independent parts first. Entanglement suggests that, at the quantum level, this assumption is too narrow. Albert Einstein, Boris Podolsky, and Nathan Rosen saw the problem clearly in 1935. Their famous paper argued that quantum mechanics might be incomplete. If measuring one part of an entangled system allowed strong predictions about another distant part, then either distant systems seemed connected in a troubling way, or quantum mechanics was missing deeper hidden information. Einstein was not simply rejecting quantum physics because it sounded odd. He had helped create it. His concern was sharper. He wanted a complete account of physical reality that preserved locality and definite properties. Niels Bohr responded by defending quantum mechanics and emphasizing the role of measurement arrangements. To Bohr, quantum phenomena could not be detached so easily from the conditions under which they were observed. The debate was not decorative philosophy. It was a serious argument about what science should describe, a hidden independent reality beneath every measurement, or the measurable structure of phenomena as quantum theory presents them. Hidden variable theories offered one possible rescue. Perhaps quantum randomness reflected missing information. Perhaps the wave function was not the final description, but a statistical surface covering a deeper mechanism. David Bohm's pilot wave theory in 1952 showed that a serious hidden variable model could reproduce many quantum predictions, though it did so by accepting non-locality. That distinction became crucial. Local hidden variables would preserve both deeper, definite properties and the rule that distant events cannot immediately influence one another. John Stuart Bell transformed the debate in 1964. Bell showed that local hidden variable theories place limits on how strongly distant measurement results can be correlated. These limits are called Bell inequalities. Quantum mechanics predicts that entangled particles can violate those limits. This meant the old argument could be tested, not merely discussed with increasingly furrowed brows and cups of tea going cold in university offices. Experiments answered. John Clauser and Stuart Friedman's early 1970s work provided important evidence that Bell inequalities were violated. Alain Specht, Philippe Grangier, Gérard Roget, and Jean Dalibard improved the tests in France in the early 1980s, including experiments where measurement settings were changed while photons were already in flight. Later, in 2015, teams associated with Delft University of Technology, the National Institute of Standards and Technology, and the University of Vienna performed loophole-free Bell tests that closed major concerns involving locality and detection. Further cosmic Bell tests used light from distant stars and quasars to push questions about measurement choice further back in time. The factual conclusion is strong. Experiments support the quantum prediction that nature violates Bell inequalities. Local hidden variable explanations in the tested forms do not match the observed correlations. The universe does not behave as though entangled particles merely carry complete local instruction cards from their shared past. That is remarkable, but it must be kept balanced. Entanglement is not magic. It is not telepathy. It is not proof that consciousness creates reality. It does not allow a person to control one particle's result and send a chosen message instantly to another particle far away. The no communication theorem protects this boundary. Each individual measurement result still appears random to the observer seeing it. The pattern only emerges when results from both sides are later compared through ordinary communication. Special relativity remains intact in the operational sense. Usable information does not outrun light. So the mystery is not that entanglement does everything. The mystery is that it does one precise thing nature was not expected to allow. It creates quantum correlations stronger than local classical explanations permit, while still refusing to become a faster-than-light message service. The universe is strange, but not careless. It opens a door, then calmly declines to let anyone run through it with a telegram. Entanglement also proved useful. Quantum teleportation uses entanglement, measurement, and classical communication to transfer an unknown quantum state from one system to another, without copying it, and without moving a body through space. Quantum cryptography uses quantum measurement and, in some protocols, entanglement to help detect eavesdropping and distribute secure keys. Quantum computers use qubits, superposition, interference, gates, measurement, and entanglement to process certain patterns of information differently from classical machines. Many body physics uses entanglement to understand collective quantum behavior in solids, magnets, superconductors, spin chains, and more exotic phases of matter. Precision measurement and quantum sensing also rely on carefully controlled quantum states to improve sensitivity under the right conditions. Even black holes brought entanglement into deeper territory. Jacob Bekenstein's work on black hole entropy, Stephen Hawking's radiation, the black hole information problem, the holographic principle developed by Gerard 't Hooft and Leonard Susskind, and Juan Maldaceno's anti-de Sitter and conformal field theory correspondence all point toward a profound relationship between information, gravity, and space-time. This remains an active research area, not a finished answer, but entanglement has become part of the language physicists use when asking whether space-time itself may be connected to patterns of quantum information. The link that should not exist, then, has become many things at once. It is a challenge to classical separability. It is an experimental fact. It is a boundary around local hidden variables. It is a resource for quantum technologies. It is a clue in the study of matter, information, and perhaps even gravity. Its quiet lesson is not that everything is magically connected in any easy everyday sense. It is more subtle and more powerful than that. The lesson is that reality is not always assembled from independent parts first and relationships second. Sometimes the relationship is part of the thing itself. Sometimes the whole is not merely a container for the pieces, but the only place where the deepest description can live. That is what quantum entanglement leaves behind. Not exaggerated mystery, but accurate wonder. The universe remains orderly, measurable, and testable. Yet beneath the familiar world of separate objects, there is a quantum layer where separateness is not as absolute as it seems, and where a link that once felt impossible turns out to be one of nature's real rules. Quantum entanglement is the link that seemed as if it should not exist, yet experiments show that it does. It is a real, measurable feature of nature, not a metaphor and not a decorative mystery added onto physics to make the universe sound more dramatic before bedtime. It challenges the ordinary expectation that distant things must always have fully separate descriptions, carrying their own complete properties independently of one another. That expectation began in the familiar world of classical separateness, where objects have positions, motions, temperatures, and directions of their own, and where influence travels through space in an orderly way. Then early quantum theory began to soften those boundaries. Max Planck revealed energy arriving in discrete quanta. Albert Einstein showed that light could behave as photons. Niels Bohr gave atoms allowed energy levels. Louis de Broglie suggested that matter itself could behave like waves. The wave function then gave physics a new language of possibility, probability, superposition, and measurement. From there, entanglement made the mystery sharper. Two quantum systems could be described by one shared state, so that the whole could not be fully reduced to separate independent parts. Einstein, Boris Podolsky, and Nathan Rosen objected that this might mean quantum mechanics was incomplete. John Stuart Bell transformed that concern into a test. Laboratory experiments, from the early photon tests to later loophole closing experiments, strongly supported the quantum prediction that nature violates Bell inequalities. Local hidden variable explanations in the tested forms could not reproduce the results, yet the meaning stays beautifully restrained. Entanglement does not allow faster-than-light messages. It does not let one observer choose a result and control another particle across space. It does not prove telepathy, mystical consciousness, or that every coincidence carries a secret quantum message. Decoherence explains why delicate quantum behavior usually disappears from ordinary view, leaving tables, people, planets, and cups of tea looking reassuringly classical. Still, entanglement has become far more than a puzzle. It appears in quantum teleportation, quantum cryptography, quantum computing, many body physics, precision measurement, and some of the deepest questions about black holes, information, and space-time. Its exact interpretation remains debated, but the experimental evidence for entanglement and Bell inequality violations is one of the great achievements of modern physics. The strongest lesson is not that entanglement makes anything possible, it is that reality's deep structure is more relational and less locally separable than classical intuition expected. The link that seemed impossible did not break the universe. It simply revealed that the universe was never quite as simple, separate, or comfortably ordinary as it first appeared.